wanted to do a few more problems on 6.11 because I don't want to assume that what the students need to do is obvious. I wanted to look at problems like number 5. You're setting all these problems up the same. The only difference is sometimes a different piece of information is using. On number 5 it says find the distance between two cities, so we could draw a little picture to help us think. And they want to know find the distance if the scale used is 1/2 inches is equal to 10 miles. And the cities are 55 miles apart. So we're finding actually how far apart they'd be on the map. Maybe we're drawing the map ourselves and we're trying to figure out how long to make a segment to represent 55 miles in this instance. So we're going to do it just like we've been doing everything before. I notice I'm going to look at my scale. Here it is. It's my map scale. And I notice that I've got inches and miles, so I'm going to make some fractions. I'm going to put inches on top and miles on the bottom. Since I circled that in green, I'm going to go ahead and write my scale fraction in green here. I'm going to have one fraction representing the scale and another fraction that's going to represent the measurements we take. Now on the scale, 1/2 inch is equal to 10 miles. Now in this case, instead of us finding the miles like we've done in other problems, we have somebody has measured and they found that the distance is 55 miles apart. So we're looking at miles here. Notice that miles go in the denominator. Before we've had the miles part missing and we were trying to find it. But here we know the miles are 55. What we don't know is how much that should have measured on the paper, how long should a segment be to represent 55 miles. So once I have this set up, this is why I really like writing inches on top, miles, why I like writing this off to the side. It can really help keep me on track when I'm working these problems and trying to figure out where to set things. Okay, so once I get it set up, I solve it just like all the other problems. I could say, okay, let's cross multiply to solve. 10 times x is 10x. And then I can say 1/2 times 55. And since that 1/2 is a fraction, I'm just going to put 55 over 1 and make it a fraction. Now if you look at that, if I simplify this down, 10x is 55 over 2. There's not really anything I can do with that to reduce it at this point, other than write it as an improper fraction, which I don't want to do because I still need to do some math here. Now, when I go to solve this, I could say divide both sides by 10. And that would be true, right? But the problem is, if I divide both sides by 10, it's kind of hard because there's already a fraction over there. So it would look like this, and it gets kind of confusing. So if you remember what we can do, we can think of, here's another way to think about this. Since you got a fraction over there, why don't we work in terms of fractions? And we'll say 10x is the same thing as 10 over 1x, because 10 over 1 is still 10. If you remember, if I make that a fraction in front there and I want to solve it, how do I get rid of a fraction? I multiply by the reciprocal. So I could say multiply both sides by 1 over 10. Multiplying by 1 over 10 is the same thing as dividing by 10, and this makes our work easier to do. Now the 10's cancel out and leave me with 1 times 1 is 1 in the numerator and the denominator. 1 over 1x is just x. Okay, now I go over here and look. I can multiply this together, but I'm trying to make my life a little bit easier. Let me reduce some things first. I notice that there's a 55 and a 10, and they're both divisible by 5. 10 divided by 5 is 2. 55 divided by 5 is 11. So now I have 11 times 1 is 11 on top of the fraction, and 2 times 2 is 4. So I have 11 over 4 is how long that would be. That's inches. You might want to change that over to, this is one of the instances where we would want to write our answer in terms of a mixed fraction. If I divide 11 by 4, 4 goes in there 2 times, and that would be 8. 11 minus 8 is 3 out of the 4 left over. So you could write 11/4 inches or 2 3/4 inches. Either way would be fine. That is, you could write it either way. The book actually writes 2 3/4 inches because we would like to have it communicated. That makes more sense to us than saying 11/4 inches. They're going to tell it back to you as 2 3/4 inches, but we'd have to work in these improper fractions in order to do the work. Do another one like that. I notice there's another one similar to that in the problems. Let's look at number, let's see, what did I notice? Let's look at number 2. It says, how far apart will 2 cities be on a map? So I'm trying to draw this segment, and I don't know how big to make it, is what the problem is. They tell me the scale is 1 inch is 200 miles. And they tell me that the cities are 300 miles apart, and I'm just trying to figure out how to draw this on a map. So again, what we're saying when we're saying proportions is if 1 inch is 200 miles, how many inches would be 300 miles? We can solve that with proportions. We make 2 fractions or 2 ratios. We set them equal to each other. I noticed from my scale factor that I've got inches and miles, so I'm going to just decide to put inches on top and miles on the bottom. You could do it opposite if you wanted to. I just kind of like to go in the order I read the information. That way I have less chance of mixing it up. And so, and then if you remember, I'm going to make 1 fraction with the scale, the map scale. We call that a scale factor in geometry, but you're used to just calling it a map scale at this point. And then another one off the measurements that we would actually need to make ourselves or something. So if I'm looking at the scale factor here, 1 inch is 200 miles. And then over here, what do I know? I know the miles part. They gave me miles, so I know that's going to be in the denominator of this other fraction that I'm measuring because miles is in the denominator. So I'm going to put the 300 there, and what they really are wanting me to find is how many inches is that on the map. So inches are missing. I'll put the X there since it's missing. Now that I set it up, I can solve it just like we've done all the other problems. 200 times X is 200X, and 1 times 300 is 300. If I want to get X by itself, I could just divide both sides by 200. The opposite of multiplying X by 200 is dividing it by 200. And we get X is equal to, let's see, there would just be 3/2, which is 1.5 or 1.5. I think the book writes it as 1.5 inches is what we do. It'd be 1.5 inches or 3/2 inches. That's all the same thing, but the book likes to write it in mixed fractions when they give the answer. So if you're checking with the book, that's how they're getting that. Students were also given a worksheet in class today that had them use proportions to solve for missing sides of similar figures. And so you can use proportions. That was the reason I gave it to them. I was kind of hoping they would use proportions just so they could see how many places you could use proportions since we were using it so much in this lesson. You could do this without proportions though. What I do though, I'm going to go ahead and do it with a proportion, and then I'll show the faster way also. I match sides up. 6 matches up with 24. The way that 9 matches up with X. So on the top of my fractions, I'm putting the first triangle, I guess you'd say the smaller one, and on the bottom of my fractions, I'm putting the side that matches it on the larger triangle. Now I could cross multiply. I'll make my life easier if I reduce that fraction. 6 goes into 6 1 times, 6 goes into 24 4 times. If I cross multiply now, 1 times X is X, and 4 times 9 is 36. That's the way to do it using proportions, and you'll eventually have to do that in geometry because you'll get problems that are not just this easy to solve. Another way you could have done it is this. Without using proportions, you could say, oh, 6 times 4 is 24. So if I am multiplying that side by 4, and these are proportional, I would need to say, take this 9 and multiply it by 4 to get the side that goes with it, and 9 times 4 is 36. I want to do one more just because I know this one I remember causing some problems on this sheet last year. If you look at this problem, it's kind of hard because they've turned the figure kind of funny, and sometimes it's hard to figure out what they've done here. So they have 10 and 10, and then this bigger figure is facing a little bit differently. On this one, here's what I would just do. in geometry, things are marked better so that you know what side's supposed to match up. They have 100 and then they have X. And it's turned kind of funny. It's not turned the same way. And here's the deal. Since we had two sides that have 10 here, we're going to say that when we match them up, those sides go together, and that if these two sides matched and were 10, then the two sides over here are going to match and be 100. In geometry, things will be more clearly labeled so that we don't have to try to make assumptions like that, but it's even hard to figure out how to turn that triangle to get it where we need it to be. One of the easiest ways to do that, I guess, would be to rotate it, take this and rotate it to the, let me look, maybe we take the big one. If we rotated the big one turn to the right and made it look like this, where the 100 was here and the X was here, that's what I'm assuming they meant for us to do here because it wasn't as clear as I'd like for it to be.